Hey everyone, Brian Beeler, and welcome to the podcast. On site again today down in lovely Raleigh, North Carolina, or Morrisville, I believe is more accurate, if we're going to be accurate. Sitting here today with Scott Tease, HPC guru at Lenovo, and we're going to tear into everything that's going on in the world of HPC, which is really interesting, and Lenovo's got a lot of innovation there from the hardware and even some software leadership as well. So we're going to talk about all that, and then also translate some of those, what's coming down the line for HPC to what that means for the enterprise as well, and talk a little bit about liquid cooling and what's coming up with GPUs and all sorts of other exciting stuff. So Scott, thanks for doing this. Great to see you in person again.
Nice to see you as well. Welcome to North Carolina.
Yeah, well, you could have welcomed me with a little bit more sunshine.
I know. It was beautiful yesterday. You probably hear that a lot.
Yes, it was beautiful yesterday, and then every time I go to Colorado, to Denver, it only snows when you're here.
Exactly.
So I don't really know what weather
what it's really
I'm
like
dragging.
there.
So we've spent the day talking about HPC, about Lenovo's innovation there. Set us up with just the high level of how you're looking at it, how Lenovo's looking at the HPC world, and just kind of level set where we are.
That's great. Yeah, so for Lenovo, we see HPC and AI and all technology in general as one of the key tenets in helping our customers solve humanity's greatest challenges. So the application of the right technologies to go solve the problems that are facing our world, whether it's climate or earthquake prediction, or it could be engineering better devices to keep us safe. Technology is the core of that. We view our role as being our customer's guide to picking the right stuff for what they're trying to do. In the past, things were fairly simple. We had one main processor to choose from. It did about 97% of all the workloads on the planet. A lot different today. There's a lot of choice out there. Customers have a lot of questions on what the best technologies are for what they're trying to do, and our role is to help be that that guide along the journey to make sure they get the right stuff.
So fundamentally, what was the decision that Lenovo made to say HPC matters and we're going to go out there and kick some butt? Because every time the top 500 comes out, you guys have been well represented for a number of years, but maybe not always that way. What was the shift to let's go get this HPC thing?
So we came over and set up shop as Lenovo HPC in 2014 after the Lenovo acquisition of the IBM x86 business. And you're right, I don't think Lenovo exactly knew what they had with an HPC team. It is a very different kind of business to what they'd done in the past with their personal devices and everything. But very quickly, they saw the benefit of being in this space. It is a high-profile space. Mm-hmm. You have very large, very public wins. The customers are doing truly amazing things. I mean, we've got North Carolina State University right down the street. They're working on prediction of what happens during hurricanes and floods. On our coastline, that's really important, using IT to answer that. We've got people that are looking at ocean currents to help predict our food sources that we get from the ocean. How are they going to be affected by climate change? Earthquake prediction in Taiwan, and you name it. I think very quickly Lenovo saw this group and these technologies as a way to make the world a better place and really embrace it, all the way up to our CEO. This whole concept of solving humanity's greatest challenges, it started with the HPC team. It's become a kind of a corporate mission, and we're really proud of that.
Well, it strikes me that there's historically been a big chasm between HPC and enterprise, and the sort of scientific educational workloads, genome sequencing, all that sort of stuff that was always at supercompute. I used to love to go to supercompute years ago and feel like an absolute moron there because you look at all these people, all these students, they're 18 years old and they're working on like stuff that's good, as you suggest. Or like Noah would have the globe up there and mapping out the weather and what's going on. I'm like, I had a breakfast burrito, I did a good thing today. But yeah, and then you had the enterprise that was like running databases and transactional stuff and SQL Server and POS systems and whatever. It feels to me that GPUs, the enablement there, AI, ML, all of these sorts of new workloads are sort of blurring the lines though between what a traditional HPC research workload would be and then what the enterprise version of that might be in more of an analytics or AI sort of way. So how do you guys think about that or start to draw the lines of those workloads, or is it too blurry sometimes to tell?
No, I think your thought about the role the two groups play, HPC and enterprise, it's very interesting. What we kind of view it as especially part of the HPC team, this is part of the pride we take in what we do. We're on the cutting edge of technologies. We know we're going to be the first in testing out new things, whether it was being first without the open source software we pioneered back in the day, or first with accelerators and GPUs and finding ways to apply those. So many firsts, so many software-defined storage and cutting-edge networks and things like that, low-latency networks. We would perfect those things and then move them as they matured, move them out into the enterprise space. So you see a lot of the public clouds today. Many of the leaders are former HPC people that took the knowledge they gained in the HPC community with these HPC techniques, and now they're applying them to public cloud. We see the same exact thing happening in the enterprise. We kind of compare it to sort of like a race car. A race car team. A race car team invents these really cool things like carbon fiber composites or anti-lock brakes or push button start. Once they get perfected, you find those on your car lot all the time. HPC's the race team, enterprise the car lot.
Yeah.
So we're pretty proud of that role. And you're right. A lot of the technologies that used to be more HPC centric are becoming far more common in the enterprise, especially for AI, both deep learning and for AI inference. And it makes it really easy for us to take the knowledge we've got and extend it out to our enterprise clients.
Yeah, I always used to say, if you want to know what's coming next to the enterprise, look at what is being shown at OCP and supercomputer,
so true.
And then in 2 years, that's what you'll be
That's
buying
what you'll be seeing.
is mainstream
Absolutely.
kind of stuff there.
Without a doubt.
I can't let the race car reference go by, though. I'm a big Ferrari guy. I don't know if you
Okay.
watch much F1, but Ferrari did finish 1-2 this past
Yeah,
weekend.
yeah.
Spoiler alert for whoever's catching this a couple weeks late. But it may not be HPC workloads, but they're certainly using GPUs for the simulations of all these digital versions of the cars, right?
Yeah, the amount of IT that's around a racetrack would blow most people's minds. So everything from optimizing the flow, dynamics around the car, aerodynamics, energy efficiency or fuel efficiency of the car, all that's HPC, very traditional, computational fluid dynamics. Those kinds of traditional problems. So people might expect that, but the amount of IT that's showing up at the racetrack, like at the edge, that's doing real-time analytics during a race, that might really surprise people. And it's a lot of the same kind of IT, whether it's back in a data center ahead of races or out during the race to try to get real-time data on what's happening with the engine. Hey, do these different things that are coming together mean something good or bad for the car? What's going on with my competition? How fast are we or how far are we behind or ahead? All those things can be looked at, through AI out at the edge, because we're putting like real hardware, real performance hardware outside the data center, at a racetrack, which is pretty incredible.
Well, we talk about edge all the time about like retail use cases and some of the popular ones, autonomous driving, but the rigs that those F1 guys show up with all over the world, which is amazing, 21 races a year. And they show up, they blow these things out. They got the whole offices. Anyone that's seen Drive to Survive on Netflix has gotten a good view of some of that background activity, right? And it's there's real computers in there doing real stuff. And the things that you're talking about, those in-race decisions, those are fundamentally business decisions, right?
Yeah, they are, absolutely.
Do we pit for wets because or inners because we think it's going to rain soon? And modeling that, and if you've got an advantage in how you model that, or fuel consumption, or what the wind shift is doing to the track in turn 4, it makes, in that world, every 10th of a second or even less, 100th of a second adds up, and then you've got real impact, right?
Yeah, without a doubt. It's the more variables you can look at to take into your model, the more accurate your prediction is going to become. Doing it there at the track versus having to backhaul it to some distant data center means you're doing it in real time.
Right.
So you're getting insight you can make decisions on right away. So humans do certain things really well. Machines are able to do things that we can't. The number of variables machines are able to do, the calculations per second machines are able to do. You combine that with human intelligence and computing power and artificial intelligence, and you really got the best of everything.
Yeah, I mean, it's absolutely amazing. I didn't know we were going to do a riff on F1 cars, but I'm glad we did.
I'm glad I like it. It's a good topic.
Oh my gosh, I'm
We can
so
talk
glad
fishing next if you'd like, but that's got a lot less IT involved.
Is there much HPC in fishing?
No, there's not.
I mean, I guess there's my. Oh, you ever watch that Big Tuna show? They've got one down here, the Outer Banks
the Outer
version.
Banks, yes.
Those dudes, I mean, they're just using fish finders and a lot of intuition, but there's a little bit of tech.
I'm sure there is. I guarantee there's people that analyze ocean currents and all kinds of things to see where they're going to find those fish.
You know the guys I don't understand, though? They catch the fish. They're allowed one a day or whatever the limit is. They drive them in, they cut it, and the guy, he does the core sample, and he's looking at the one piece they cut out, and he's like, that's a $12 a pound. That's such baloney. I've watched 900 episodes of that show, and I still, and everyone around will be watching it, and be like, oh, I've 14, 12, and we're all wrong. I mean, I don't know how these guys divine the cost of a tuna.
It all matters once it shows up in Tokyo, what they're willing to pay for it, probably.
There's that.
Yeah.
So now F1 riff and tuna fishing. Okay, but we'll keep going. Eventually back to technology.
We're off path, I think.
Yeah, a little bit.
I know.
So from a technology standpoint, I think it's interesting what you guys have been doing, I guess over the last decade with Neptune on liquid cooling. The HPC universe seems real willing to embrace whatever it takes to be able to use these resources to their fullest. What's going on there with liquid?
Yeah, it is hard to believe. It's been almost 12 years since our first install of a liquid cool. Sorry, it's been almost 10 years. You're right. It was 2012. I apologize.
Right.
It's been a decade since we started with our first warm water cooled supercomputer at LRZ in Munich, Germany. And I remember I was part of the team that did that. We were freaking out a little bit. It was 9,700 nodes, liquid cooled for the first time ever. And it got us nervous, but it's been an incredible story ever since. The customer's been happy. Some of those nodes are just now coming out of production.
Wow.
That's how long it's been in production. But what we're seeing with Neptune and with liquid cooling in general is that the reasons to go towards liquid are even more than what it was a decade ago. So the reason that LRZ went there was because in Germany they pay pretty high power costs. They're probably paying about 18 euro cents or 20 US cents per kilowatt hour. That's double what we pay in the United States. It's like 3 times what you might pay in, say, Denmark. So their power costs were very high. So every time they could drive power consumption out, it had a pretty big benefit for them on their energy bill.
When you're talking about that many nodes, right?
Oh yeah, we're talking
so
megawatts
incremental,
of power.
but it just cruises at
hundreds
scale.
of thousands of euros, potentially monthly in energy. So it's big. So that's what drove them originally to do it. Now what we're seeing, that same thing still remains true. The whole energy, bill and the cost of energy still matters. But we're seeing a lot more customers adopt liquid because they see it as the way to unlock performance that air can't do.
Okay.
Processors that air can no longer cool, GPUs that air can no longer cool, or at the density that they would like them to be in. They built this data center. It was supposed to house, 10 racks, but now I can't even fill those racks up because I've run out of power or run out of cooling capability. Liquid cooling will extend that data center. The newest theme that we're starting to see is around sustainability. And that is one that's been surprising to me on how broad it is globally. People see liquid cooling and its advantages from a energy efficiency, carbon reduction kind of standpoint. It's like resonating universally, like globally. So we're seeing lots of installs now in the U.S., all over Asia Pacific, China, you name it, and continued there in Europe where it all started. So it's been more reasons to go there.
So talk a little bit about where liquid helps you, because you're putting more stuff in these boxes. So you're putting 8 GPUs in it. You've got 2 x86, high end in some case, CPUs. You've got storage, NVMe going on in there. So how does liquid change the dynamics of where power comes from? Obviously, in some of your fully liquid systems, there's no fans. So that's a savings. And maybe that's the most obvious one. But what are some of the other dynamics there?
Yeah. So you think about it. You got a couple of bad. It depends on how you look. You have some trends going on in the server. One is higher performance, but also higher power. You're seeing the server designs pack more in than ever before. Like the new CPUs from Intel and AMD have more DIMMs per socket than we had in the past. So you got more components. The components are smaller, and the vendors are asking us to keep the parts cooler than they did before. Their T cases are dropping. So you take high power in a small space, needing to be kept at very, very low temperatures, and it means you've got to have massive amounts of airflow going through the system to keep those parts from overheating. The more airflow you need, the higher the fan power is going to be. And at some point, the budget that's going to go just to run your fans, not to do math, not to move things around a network.
Just spin
Just
air.
to spin air and move air out the back of the server is going to get so high, you're going to realize that there's better ways that you can go, and liquid cooling is there to help. So we have, as you mentioned, we have some direct cooling designs where we bring liquid into the server itself. It cycles over the processor, the memory, the voltage regulation, the I/O device, even the media. We're taking over 90% of all the heat being generated by the server out. It's super efficient. The systems run perfectly quiet. We could have one sitting behind us, Brian, and we would never even know it was there. It could be running LinPack, and we wouldn't even know it was there, because you're not having to blow all that air and make all that noise from the signature of the fans. It's huge power savings. It's environmentally beneficial because we're not having to chill the water that goes into those. We can use warm water, so I'm not having to pay to chill or pay to air condition. It just continues to feed on itself the benefits that we see with the liquid cooling.
Well, and what impresses me the most about that is that you've got 1U servers, liquid cooled, that have how many GPUs in the 1U?
4 GPUs and 2 high-powered CPUs in a 1U tray.
That's amazing.
Fully liquid cooled. It is amazing.
For density is insane.
One of those racks, it's quite impressive. I'll tell you a little bit about that one because it is really interesting. It's a product that we call the ThinkSystem SD650-N. The N is for NVIDIA. It's got 4 A100 SXM GPUs in it, very high performance, and 2 high-power Intel Xeon CPUs in it. That tray, we can get 36 of those in a 42U rack. It's going to consume about 80 kilowatts of power, which is a lot of power, but that one rack will get you on the top 500. That's how much performance we're talking about in a single. So think,
amazing to imagine
one floor tile wide, 2 floor tiles deep, and you could potentially have a supercomputer on your floor, and all liquid cooling and running nearly silently. So it's pretty incredible.
That would get you top 500.
That would get you on the top 500 with just a single rack. 36 of those nodes. That's a combination of the power of using liquid to create the density that customers would like to see, and the new components we're getting from Intel and NVIDIA are just unbelievably good.
How big was your first top 500 cluster? Do you remember?
Oh man, it was at the University of New Mexico, and I don't even remember how many teraflops it was. It was not much. But that was like 2004, 2000, something like that.
Yeah.
It was, it would fit in less than a single server nowadays. So, but one story I like to tell people is I was also with the team at IBM when we broke the petaflop barrier for the first time, and that took hundreds of racks, hundreds of miles of cabling, high-speed networking cabling. It was hundreds of $1 million to do the petaflop. I can do the petaflop in less than a rack now with that new system. So we've come a long way in the past 10 or 12 years.
Not quite as expensive, I hope?
Not quite as expensive, thankfully, yeah.
So when we think about how this technology continues to trickle down, the enterprise, for now, will have some reluctance to go to full water because it's scary. What are people concerned about?
I think, when we have conversations with customers about, liquid cooling, we have two reactions. Reaction one is, if you grew up around a mainframe, it's like it's about time that you Intel guys or gals have grown up and you're finally using liquid cooling, because it was a good idea back then and it's a good idea again. All good ideas get recycled,
Yeah, funny
right?
how that's come back around.
Exactly. Right? If you grew up in the PC days, the concept of electricity and liquid together kind of freaks you out. And I get that. I get it. So what we need to do is we need to show the enterprise clients that liquid is simple, that it's easy. It doesn't have to involve like major changes or customizations of the data center. We can do it pretty simply and create a liquid-cooled section of the data center. We're also showing off in like our SR670 server that we can do liquid inside of an air-cooled device. So we are not using liquid to take the heat out of the room, but we're using liquid to take the heat from the part. I'm worried about the GPU overheating. I use liquid to carry that heat away because the liquid's super efficient at transferring heat. I move it out to a little heat exchanger or like a radiator, and I handle it there. And there's huge value to that. My hope is that we bring in something like our SR670 V2 in, we put it at a customer site, and we tell them after it's running, we say, that's a liquid-cooled server. And they're like, no, it's not. There's no plumbing to this. And we open it up, and they see that heat exchanger in there. They get comfortable with liquid cooling, and it goes from there.
So I want to talk about that, but I will say that some of the apprehension around water and electricity, I grew up in the 80s, and there were two things that were probably going to kill you: quicksand and electric eels. Okay? So if you have that mentality,
Yeah.
you know, even in Cincinnati, two things that were probably going to get me based on the television shows that I watched at that time. So once we can get past the electric eels probably won't kill you, then maybe it'll be easier to adopt this.
Yep.
So this,
Even I'll say even a lot of our home gaming people that buy Lenovo workstations that do gaming, they'll do some liquid cooling in their GPU at home. It's become more acceptable and people get it. The challenge is just to make it robust enough and last long enough so it has the lifespan that a data center client
that would carry with the server, right?
Exactly. That's going to be around long enough.
Well, yeah, I mean, the analog for PC gaming is obviously there. Those radiators and liquid cooling's been used on CPUs for a long time, GPUs for quite a while.
Yeah.
We're starting to see it show up on SSDs now, so on the M.2s, little extra radiators you can add. DRAM maybe a little less so in the client space, but definitely coming.
Yep.
Because when we go to PCIe Gen 5, Gen 6, and all these components keep getting faster, more power, I mean, there's going to be no choice.
Agree.
So you started talking about a 670 V2, and we've got a couple sitting on the desk for those watching. But the really neat thing to me is that while you've got a common product with the PCIe slots for regular edge cards, for accelerators, or I guess I/O too, if you want.
Yeah, it could be any PCI connected device.
Okay, so anything. You've also got this one with the closed loop cooling for GPU. So let's talk about that a little more specifically, because it does resemble more of a gaming rig, in that one notion, right?
There's many aspects of it. You're right.
So what's going on there that is so unique in that radiator design?
Yeah, so the way I like to describe it to people is if you are still driving a gasoline-powered car, not an electric car, you've got a radiator in your car. Yes. The way the radiator works is you've got a coolant that goes around the hottest components in your engine, the cylinders. The liquid takes the heat away from those cylinders, moves it to the radiator. When you drive down the street, air goes through the radiator, takes all the heat from the cylinders that's been transferred from the cylinders out from the radiator out to the universe. It's the same concept we've done inside of this server, but on a much, much smaller scale. Instead of cylinders, we have GPUs. They each have a cold plate that's over the top of them. We pump liquid from the heat exchanger to the GPU. What's nice about that is it moves the heat away very efficiently. I get it inside that radiator. I spread it out nice and uniformly. I can use bigger, less power-consuming fans, blowing at lower speeds, lower acoustic signature, to help then move that heat out of the heat exchanger and out the back of the server. So it's a fairly simple concept that's proven in like everybody's car, but applying it inside a server we think is a really unique approach to handle the heat that's being generated from these devices. The GPUs that can go in this chassis right here, easily 400 watt devices,
right?
And there's 4 of them,
right.
So 1,600 watts just the GPU power, in a space that's about 19-inch rack width wide, and only a few inches
shallow
deep.
too,
it's very, very shallow,
right?
So it's great to have the liquid to move that heat away so quickly.
So you're right, though. First of all, if you didn't know it was in there, you wouldn't know until you turn it on, and it's still going to make noise. But it's going to be a heck of a lot quieter.
It's not going to sound like a jet taking off, like some products that just
we have plenty of those.
Yeah.
Sometimes there's no choice. If you've made that design decision, then you have no choice but to spin faster, especially in super dense servers. So that's one thing. You talked about life, so it's going to match at least a 5-year, and probably longer, but it's going to match a 5-year kind of warranty service window.
Easily, quite easily. In fact, the team's designed that, right, just to give you an idea. We wanted to make sure that even after a 5-year life, the most you would ever see going beyond 5 years is a 10% performance potential of like going beyond that, because maybe the pumps get old or we lose some of the liquid, things like that.
They don't go to zero.
They don't go to zero.
They atrophy a little bit.
Right, exactly. But it's still going to last for a very long time, beyond the use case of most of our data center clients, for sure.
So as we think about enterprise computing, though, I mean, obviously this can go in anyone's rack and be in the enterprise, but do you think then that that's sort of the gateway drug then to start to adopt liquid? And is it going to be the GPU, or would it be maybe CPUs or other components where you could do a closed loop? Yeah. What else can you do with that, I guess?
Yeah, so I think you're going to see a lot of this thing. So for the engineering team here at Lenovo, we've got 2 things we're trying to do. One be the very best at liquid cooling that there is out there, showcase all the benefits of the warm water approach that we've taken all the, the high heat capture, the warm water cooling. We want to make sure we do that. The other side of what we're doing, using the same engineering team that works on liquid cooling, is also keep the air-cooled environment going as long as we can, as making it as energy efficient as we can. So that little device that does GPUs today, we have a very simple, kind of much more streamlined device that does high-powered CPUs today. And we're looking at 1U and 2Us that have that same exact radiator heat exchanger in the back, because we want to be able to do the 350, the 370, the 400 watt CPUs that are coming this year and beyond as we go out in time.
It's the beyond that's kind of scary from an engineering perspective, right?
So what's ironic, I think, for a lot of people is they often think of heating being a room level problem, because it has been. It's like you could design a 1U server and you put it on the desk right here in front of us. You power it on. You have your guy Kevin power the thing on, and it runs forever in his lab.
I know how to power on a server. How dare you?
Sorry.
How dare you?
Now you're going to be mean to me for the rest of the interview. So Kevin powers it on, or you power it on,
right.
And it runs forever with no problems on that bench. The problem came in when you put it next to 36 or 40 of its friends, and the room would overheat because the room couldn't handle the heat output of all those devices simultaneously. The problem we're running into today is the components we're getting are so small, they're so high power, they're so densely packaged in there, I can no longer get the heat away from the part fast enough before the part will potentially overheat. Or even if it doesn't overheat, it's going to go into these extended temperatures that's going to cause early life failures, things like that. So the liquid cooling helps us move that heat away from the part quickly. I move it from an area where it's going to cause me problems to an area where I can handle it and better deal with it. And that's the beauty of the liquid.
Well, I mean, from an endurance standpoint of those components, it should be dramatic.
It should be. And it's hard to tell. So we've been running this for a while. So you think we'd have really good stats on air-cooled versus water-cooled and the things.
Oh, for AFR or whatever?
Yeah, for like lifetime and Fallout and everything. HPC people, they're just so abusive to the gear. They're running at 100% all the time. And you give them an extra processor, it'll be in 100% utilization instantly, because they will consume everything you give them. So it's like a balancing act of how much did that liquid save us from having early life failures by keeping the parts cool, versus the increased risk of fallout based on this crazy utilization rates.
Well, storage is one that I know some of your servers in this line have quite a bit of storage built into them, depending on the need. But storage is one of the first ones to fail under heat. Those controllers on the NVMe drives, if they get too hot, they'll throttle, but they'll just fall out and just disappear. And we see that in servers all the time when we're hammering them, even with just regular transactional workloads. We can, under certain conditions, make them fail. In the HPC world, it must be data analytics or just ingesting that data set and manipulating it. It could be torturous.
I mean, there's so many components. So again, I often go back to like in the past. It seemed fairly simple in the past. You design a two processor, server. You had PCI lanes out the back, and whatever PCI card you could find, you could put it in there, no problem, whatever. Nowadays, there's so many of the components that have special, very low T cases, or power consumption's going up really quickly, like networking. We would consider networking to almost be like throwaway wattage, meaning it was so small, it was there, but did it really matter? The new NDR cards that'll be coming out later this year, they could be 40-watt cards.
Yeah, times a couple, right?
Exactly. So, you think, I've already got this server running really hot and I'm blowing hot air out the back, then I put my InfiniBand card out the back. Can I still keep that 40-watt card from overheating? Those are the kind of questions that we've really got to answer, and that's why the engineering team spends so much effort on how to keep these things cool and keep them safe from the thermal challenges like what you talked about.
Well, we talked about, I don't know that we called it by name, but Neptune, your liquid cooling skunk works down over the road in Building 7 there. But they have been working at it. We talked about it for 10 years. But why do you think, was this another conscious decision that you guys wanted to get out ahead at this? Because you have competitors. We didn't even say this is a 3U box, the 670 V2. Most of these that are air cooled can't conform to that. I think they're
4U
or bigger in some cases.
And a lot of times, even at 4U, they may have limitations on processor or memory or networking. We still have all the capabilities that we can deliver are available in this box because of the liquid cooling.
Right, so you're not having to back down.
You're not having to
on
back
CPU
down. You're not having to
SKUs.
limit number of memory or numbers of PCI cards. It enables quite a bit.
So go back to the
Yeah.
conscious decision to look at liquid cooling
Yeah.
as an avenue.
I'd love to be able to tell you that it was 100% like a Lenovo back in the day. It was an IB. I would love to be able to tell you that. It was a partnership, honestly. It was a customer, LRZ, that was super passionate about finding ways to make HPC more energy efficient. They were that way back in 2012. They are that way now as we work with them today. They're constantly working with us to push the envelope about what can be done on heat transference or high level temperature operation, 45 degrees C, incoming air, things like that. So they challenged us, the team came through, and we just saw the benefit of it, and we just continue to invest in over time. We've always had good success with it, but that success is just amplified over the past 18 to 24 months. It's just gone global, and it's beautiful for us to see.
So you talked about room temperature. And so in our lab, that's what we fight. We've got 8 racks of gear, 6 in the main lab, and then 2 in a downstairs lab, which is weird. You wouldn't do that if you were a sane person. And we're in Cincinnati, so we're open air cooled most of the year until it gets real hot. And then we have to start making some decisions about, in our world, we're not production, so we can shut some stuff down if we want.
Yep.
And we had to get creative in how we use the exhaust. So in the wintertime, we recapture and circulate the heat from the data center or from our lab throughout the building. So we don't ever run the heat. So Cincinnati, it can be 0, and we don't have to heat our building. So that's kind of neat. Yeah.
Oh, wow, that's interesting.
That's all. There's a lot of your gear in there too. So this Think server is cranking through there. So that's kind of neat. But there is a limit, and when it gets hot, there's a limit. And as the systems become more powerful, then we either have to run fewer that are stronger or whatever, start to make decisions. So in our case, or in any other enterprise case where they see that writing on the wall and say, I don't want to invest another 6 figures in cooling this room with more units on the roof or outside or whatever, because that may not be tenable, especially with a ecological mission or directive in your IT department. How do we start? Has liquid cooling gotten simple enough to just buy the what do you call that thing? The
CDU.
The CDU, this big chunk and drop it in there? And then what other implications are there? How much retrofitting needs to be done to access the water? And
and that's a good question. Most of our new installs today are going into a traditional air-cooled data center.
Yeah, I mean, I would assume so,
which is kind of surprising for some people, but we're not talking about having to do a bunch of retrofitting of infrastructure and capital outlays or anything. We have 3 ways that we can approach an install. One is your very big system like LRZ or Max Planck or Korea Meteorology. You do a data center level solution. It sits, the gear, the transferring gear for the CDU sits somewhere outside the data center in cheaper space. You keep the IT in the data center. That's one way to do it. The other way, in the more common way, probably the most common way we see today, is you set it up as rows. We have a CDU that's rack-based. It literally looks like the exact same size and shape as a normal Neptune rack, sits right next to it, and it can cool the 6 to 8 racks next to it. And I just plumb from the CDU to the racks back and forth, and that's my solution. I'm not having to run piping under the floor or anything. It can be just in the racks next to it. So it's really, really simple.
Now that's probably the magic for increased adoption, right?
Then the real magic one that we're really excited about this year, we're going to be releasing an in-rack CDU that can do I think it's 80 to 100 kilowatts of power in a single rack. So you have like a small device at the bottom. That could be liquid to liquid or liquid to air.
I may have seen that earlier.
And you probably did on the tour. All the servers that are in the top of that rack are cooled by liquid, but we're transferring it inside the same rack, and I can either take that heat to air out into the data center room if you want, and to have no plumbing, or I can plumb it to my data center and have it carried away in liquid that way.
So that one can be entirely self-contained.
It could, and our hope is that customers, if they use the one that's liquid to air, they see it as an air-cooled solution that just happens to have liquid inside of it, just like this, our 670 here has it.
Well, I mean, when you think about some of these edge locations, like an F1 truck to be able to do those analytics at the edge. That would be.
It would be perfect.
That would be nice.
It would be perfect, absolutely.
Because the electricity required to cool that stuff is a challenge at some of these sites.
It'll be 40%, yeah. So the cooling power to cool the server is generally about 40% of the server consumption itself. So if you got a 1,000-watt server, it's going to be 1,400 watts by the time you add air conditioning to it, just to handle the heat rejection from the server's heat. So, the other nice, you talked about heat recycling, and I didn't know you were doing that. That's pretty cool. Kind of hard to do that on a big scale with a lockdown data center and production environment with air cooled. And the reason why it's hard is two reasons. One is in an air cooled data center, you typically start with chilled air. So you start with 25 or 28 degrees C air or something like that.
You have to do that
70s,
in American for me.
Around 70, something like that. It's cold, okay? It's cold. You need a sweater at the front. You need a sweater at the front of the rack. You go around the back of the rack, and it's super hot back there. You feel like your face is going to melt off.
You need board shorts and a
right.
tank top.
It's a totally different environment. It's like Florida in the back and Alaska in the front. So the problem with that is you've had to cool the air to go into it. So even though it feels hot, it's hard to make really good use out of that air. One, because it's bulky. It's not like highly concentrated energy. The other is it's not as, even though it's hot to us as humans, it's not that hot as it has so much stored energy that it's reusable. The liquid loop, if you go with a liquid cooled server, the water goes in unchilled. So it goes in at like 125 to 130 degrees Fahrenheit, about 40 degrees Celsius. It goes in that temperature, so you don't pay to chill it. When it comes out, it's even hotter. It's 50 degrees Celsius. That actually has enough value to it, enough energy stored in that liquid, we can make use of it. So you may not need heat in Cincinnati all year long, but you probably have hot water running all year long. We could somehow find a way to transfer that heat to your building hot water loop and replace some of the cycles on your hot water heater. So, in essence, you'd turn the computing environment into an exotic hot water heater that also happens to do computing, and you make use of the waste heat that way by recycling it to another purpose. If you're at a university, maybe we heat a pool, something like that. You're in Chicago, it's cold, heat a pool with it. Instead of, paying additional energy costs to go heat the pool.
To make water warm,
Yeah, right. Use the supercomputer's water to do it. We're really excited about that.
Throw a spigot on the side of the rack and maybe a little shower head, one of those nice Kohler dudes on the side there. That might work. Well, I mean, it's all super cool dealing with the heat, right?
Yeah,
and
it is, yep.
And if I've learned anything with working with your team today is just the impact of fan utilization in design. I mean, it's so, we're used to the noise, we're used to the airflow and just kind of stopping.
You're around this stuff all the time, having to work with it on a bench.
But you just stop thinking about it at a certain point. When you're talking about being able to take the fan and instead of running it at 98%, to be able to run it at 20 or 30,
huge power difference.
Your power consumption is very measurable at that point.
Absolutely, it is. So, we've been showing trend curves lately about power consumption of the fans. People think of fans as kind of an afterthought. They're actually
they're just there, right?
They're just there, right? You need them. The problem is they don't do math. They don't stage things. They don't move things around in the network. They're just there to keep everything cooled. So as long as the power consumption is small, you don't care. The problem is the power is getting really large. So 5 years ago, fan power was maybe 4% of your power budget on your power supply. So if you had a 500-watt power supply, 4% of it was going to your fans. Did I care too much about it? I probably could live with it.
Too small, right?
Too small. These days, it's 10 or 12% of your budget. So that same 500-watt power supply, 50 watts of it or more is going to the fans. In a couple of years, as these trends with higher power, lower T-case, more density, smaller components goes up, that could easily rise to a fifth or even more of your power budget. So, I mean, it's going to be a problem for the industry because people are going to wake up to the fact that the fans are bringing zero business value.
Right.
So if we can do something smarter with them, let's do something smarter with them.
Is there any fan innovation?
Well, I think, what you see in the server here, I think is a really great innovation. It's just a way to allow the fans to work more uniformly across a bigger surface area. Yeah, so, instead of having the fans do these very aggressive ducts and things like that to try to force air through certain spaces, I move the heat to some other location with the radiator exchanger, makes the fans work much, much lower. So, you see a lot of designs today with larger fans instead of lots of small fans. One bigger fan moves more air at less power than lots of smaller fans. So you see a lot of design trade-offs looking at those different ways to go about cooling. But it's a big part of the power budget, and it's something I think our customers could look at and make changes without impacting anything to do with how their business is running.
Yeah, we didn't talk about it a lot in this 670 V2 config, but the fans are kind of center back or forward, depending on your perspective on this.
Yeah.
And that radiator is just parked right next
in front of it
to the fans.
Yeah.
And so it's already it's aluminum. It's already distributing some heat just naturally, and then the fans are there just ready to
pull it through
to crank a little harder on that.
Yeah. The nice thing about it is the fans in the server run so slow that the server runs. It's not silent, but it's very quiet.
Yeah.
They're consuming a lot less power because the heat is all dispersed evenly through a radiator that's almost as wide as the server chassis. So we're not having to pull it through just a very narrow heat sink between some DIMMs or something like that. It really frees us up to do some unique kind of things. So, the other thing that we haven't talked about, we looked at hardware today, and you saw the thermal lab. We haven't talked a little bit about software, but energy management software. We have a couple of different things that we do with energy management software that can look at how the server's running to optimize not only for performance, but also for power efficiency and power use, both at an individual server level with our xClarity Energy Manager, and also at a cluster level with our Energy-Aware Runtime Scheduling software. It basically, the Energy-Aware Runtime Scheduler is really cool. It'll profile a job for you, and it will allow us to scale down things like frequency of the processor to minimize power consumption without impacting the time it's going to run that job. The software will turn things off that have power state controls on them, so that when you're not using a device, we power it down, so you're saving power consumption. So, both those things can easily save 5 to 10% of your power consumption just through managing unneeded components or over spec components when they're not needed, without impacting the business results you get from it. So there's a lot we can do to help our customers lower their power consumption, lower their power bill, but also lower their CO2, because they're not having to buy that power that was generated when they burn fossil fuel to make the electricity.
Yeah, that's it's an aggressive mission, but when you look at it at scale, all of these incremental changes makes a real big difference.
It adds up. It really does. Yeah.
So as we look forward to what's next, as you look at your world in HPC and to a lesser extent how that eventually impacts the enterprise, a year or two out, what's Lenovo most excited about in terms of what's coming down the road from an innovation standpoint?
Yeah, I think the biggest thing that I'm excited about is we've actually given this thing a name called From Exascale to Every Scale. And the concept behind this whole mission is we think of it as sort of an engineering commitment to our customers, that we're going to design even our highest end systems in a way that anybody can consume them. So let's take our systems at Korea Met, the people that do the weather forecast for all the people of the Republic of Korea, or at LRZ, or at any of our large supercomputer sites. That same exact technology, that same exact footprint, the rack shape, everything can easily go into our small university clusters or a small research site or even a corporate user. It fits on the same 19-inch rack. It uses the same kind of traditional high voltage power, nothing strange there. You have the choice of air cooling and water cooling. The floor weight loading is not outrageous. It'll fit through your door. It'll fit in a freight elevator. We're really focused on trying to take all these exascale innovations and make them digestible for people of all sizes. That's something we're pretty proud of. I think we're in a unique position to do that. I see pictures of some of the exascale systems that are getting installed right now. The racks are massive. Now, it's cool technology, don't get me wrong, but the racks are huge. They're not going to fit in most people's data center. They're 2 or 3 wide, normal racks wide, and more than a rack and a half deep.
Right.
And they're well over 2 meters tall. They're not going to fit in most people's data center. So hard to consume that if you've got to rebuild the data center for it. If you're an exascale site, probably fine. You can afford to rebuild a green site to build an exascale system. But what we want the exascale building blocks to be used by everybody, from small HPC down to our enterprise clients, even out at the edge.
Yeah.
Yeah.
Well, that's cool. I mean, I think this is a great conversation. The leadership that Lenovo has shown in the HPC space, obviously, you guys are well committed. I mean, you're all in on this thing, especially when you look at the top 500 every year and see the wins there. And what's your count of the top 10 these days?
We got 180 total top 500.
Yeah.
We've got 7 in the top 100. I think all of the 7 in the top 500 are Neptune cooled systems. We've got almost maybe 60 or 70 in the top 250. So we represent the entire top 500, and that's the beautiful thing about it. Not just the big ones, but pretty much up and down.
Well, there's no doubt in my mind that with the technology coming down, that liquid cooling is going to be the path forward, whether it's HPC or enterprise. So what you're doing here, I think, is just so neat because it's a vision into what will eventually get there. The contained rack systems sound really neat. Just to get past the fear of having to run. If I'm not, maybe I'm not even on an elevated floor. Then how am I going to plumb this thing? That may be one way to go, but there may be some other paths that are a little less onerous. So that's pretty cool. And great chat. Appreciate you doing this.
Thanks, Brian. Thanks for coming down. Man.
Happy to do it.
Thank you.